the periods of the periodic table, and now we were looking towards each group separately. So very briefly, what we have seen, obviously, the general trend goes along the line that our orbital energy increases down the group, and that you have already studied before as well. But here our interest was such cases, especially where there lies some sort of exception. And here we have seen from 3s to 4s, this sort of transition happens where atomic number is increased by 18, right? And here again, the general trend follows as we go to 5s, and then moving back to 6s, there is again insertion of these 14 F block elements, as well as the relativistic effect explained by this phenomena where RH we have already seen is a constant, but it contains the mass of electron in the numerator. So as the atomic number increases, the rotation of electron, the electrons circulating around the orbit, its speed increases. So when speed approaches speed of light, this relativistic mass will be greater than the rest mass, briefly. So when this mass is increased, with this negative sign means the energy becomes more negative, or it will decrease. So that's exactly or precisely what's going on in this period. This particular one, right after the barium, when the atomic number starts is 71, the atomic number is increased considerably, and now the relativistic effect is prominent. One more idea to cover, that this relativistic effect is only prominent in s orbital due to its higher penetration. All right, so let's move forward. So whatever we have seen till now, if you guys are good to go with the orbital energy trends, हमने ये वाले trends भी detail में देखे थे along the period. If you are good with that, same trends are being translated towards atomic size, ionization energy, and other parameters, and we'll see in a right now. Okay, so all right, so this was the trend of the radius we were looking at, and again we have seen this was the radius equation derived by Bohr, and obviously he didn't have this factor. He was using atomic number here, but since we have seen that Z effective is the basically gives the actual picture of the atoms because of the effective nuclear charge, it entails the shielding as well. So we know there is shielding. That's why the outer electrons won't experience the whole nuclear pull towards the nucleus. So when the trend was modeled using this equation and compared to this experimental value, so why we are still looking at some well, the trend does form some sort of model that how the radius trend will decrease or forms along as we go around the period and groups. But what's the main factor that is causing some deviation? And it's the same that when you were considering this is the nucleus, and you have fixed orbits around the nucleus, right? When you're considering these fixed orbits, if electron is here, suppose, then obviously it has no probability here or here, right? Because at that time we were considering in particularly this equation, we were considering that there is a fixed radius. But now we know the actual picture goes along the RDF, where even I'm talking about 2s, suppose, it does instead of some most probable radius here, it does have some probability here. So when atomic number increases, obviously the orbital shrinks, there is no doubt, but it won't follow the exact trend because the atomic radius is no longer at exact particular value. It is a probability distribution. That's why it won't follow exact this model. All right. So that's the same idea that is being discussed here again, that what's the trend of atomic radius we have already seen in orbital energies when we were talking about similar, discussing about the simple periods or groups. For example, here we have the group 1. You have seen, you are already taking into account the increase in the atomic number and the shell, the atomic radius is being increased, and that's pretty much what we have seen, the normal trend. Again, as we move along the period, here you can see hydrogen, helium, it is decreasing because the shell is the same, and the same reason goes for second and third periods. And what happens exactly when we have already seen in orbital energy trends that the trends some sort of cause deviation when we incorporate d block elements, and that's exactly what's being translated here as well, that that as soon as the d element starts, uh, the decrease in the radius is no longer the same what we were looking into the simpler groups like sodium and lithium in the second and third groups. And that you already know what's going on exactly, that there is 3d orbital and then there is 4s orbital, right? So electrons are being added in d right now, and they are causing some effective shielding to 4s, the same reason we have discussed earlier in orbital energy trends. So that won't let the 4s to decrease appreciably once the atomic number is increasing, and that's the same idea that is being translated here. ये सब हम orbital energy trend में देख चुके हैं. Same goes for other d block elements, right? And you have seen in the recap, we have seen that the energy of 3s and 4s, right? And that's again the same replicated here, that once the atomic number increases, here it was increasing by 8. Once we move from 3 to 4th period, it is increasing by 18. Once it's increased by 18, incorporating these d block elements, shell is increased by the same number, which was 1, as in the case of this one and this one. So that's why the gallium has less atomic radius compared to the other groups. So all right, so right, so we were talking about gallium, and then as we move forward, you know that from gallium to this period, which is 3rd to 4th period, right? So now the atomic number is increased by the same amount. It was increased by 18, and here is increasing by the same amount. That's why the same trend is being followed. All right, so now moving forward from 1, 2, 3, 4, 4th to 5th, sorry, 5th to 6th period, what happens exactly? We have seen again the same idea happens here as well, where instead of d block elements, now there are 14 f block elements incorporated here, causing the atomic charge to increase by 32 instead of 18, which was increased previously, right? So now again, you can see that it's not the increase, it's almost same, or you can say increasing slightly. So it's basically not increasing by the same amount, and the reason stays the same, right? So any questions till now? All right, so these are some of the, again, barium. Okay, so this is about second group, right? And you will see that any sort of deviation will be corresponding to either this idea that 18 atomic numbers are being added, obviously the change in atomic number is different from the previous group, or there is relativistic effect. So from barium towards radium, so this is barium here in the 6th period, and then there is the 7th period here, which is not shown, but here is the radium. So ideally its atomic radius should be less, right? But here what happens, that the atomic radius follows general trend. It is increasing as we go down the group, but it is decreasing in case of radium as you go from barium towards radium. Why exactly? Because this is s block elements, the outermost shell is s, obviously orbital, and atomic number has been increased by a significant amount, right? And due to for general idea, you can remember that if it is increasing, it is 71 or higher, the relativistic effect will be prominent. So in case of radium, the atomic number is 88, right? And now the relativistic effect is prominent, causing the decrease in atomic radius, which is obviously deviating from the general trend, right? So let's go through this data here again. This is boron, aluminium. It's the third group, right? So what exactly is happening here? It's the third group, and as you go along the group, down the group, the atomic radius is increasing. 85 to 143, 135. So that one again, we have already spotted it before, but now we have the actual data. We can discuss it quantitatively, that why it is decreasing. And I've already repeated several times that the reason stays the same, that the atomic number has been increased by 18 and the shell was increased by 1, as in case of every other period. So as I was moving from this to this period, which was first to second, second to third, the shell n was increasing by obviously 1. Here it was 2, then n is 3 here, n is 4 here, but atomic number was increasing by 8 here, but it is increasing by 18. Okay, now as we move forward, this is the fourth period having gallium in it. Next period is this. You can see that atomic radius is increasing, and then we have this. So that's interesting, really interesting to note that these two elements, when I am talking about this specific group, so obviously as I move towards here, there are f block elements incorporated here, but as you can see, the atomic number is increasing, but it is not increased by the significant amount as we have seen before. So you have seen that it was decreased here. Why? Because the valence orbital was s. Now the things are different. The valence orbital is p. Relativistic effect does plays role here. It is playing role here, but it is not as prominent as in case of s. And that's exactly what this data suggests, that the atomic number is not decreased in this case, unlike this one, because here the valence orbital was s, here it is p. So that was all about atomic radius. If you have any questions, you may ask now.
Can you explain? Can you explain why relativistic effect is prominent in S and not in P?
All right, the reason is actually the higher penetration of S, right? Because it penetrates closer to the nucleus, any s orbital. Even if you draw 6s, maybe yeah, it has five radial nodes. It does have some probability here, and that's sort of the idea. You can draw s orbital. So this higher penetration, when the atomic number inside the nucleus, obviously the proton number increases significantly, this higher penetration is the main cause that shrinks this s orbital more. And that's exactly this data suggests as that as well, that you can see 5s, the 6s has less energy than 5s, but here they have plotted p orbital as well, and this shows that they are approximately same, right? So in simple words, the answer to your question lies that it has higher penetration. That's why it is affected significantly when the atomic number is increased. So I hope it explains.
सर उसमें जब एफ ब्लॉक एलिमेंट्स ऐड होंगे तो उसके साथ साथ उसमें इलेक्ट्रॉन्स भी ऐड होंगे दरमियान में, तो वो शील्ड नहीं करेगा उसके न्यूक्लियर चार्ज?
Yeah, so good question, but keep in mind when we are rationalizing these trends, the first factor you need to know as you are moving along the period, the main factor is this one: atomic number is increasing because n is constant. So, but as you are moving down the group, atomic number is increasing. This will obviously decrease the energy, but the significant factor is this n, right? So n is basically when an extra shell is added, that basically causes the electron to circulate away from the nucleus, and that's the deciding factor. So in simple words, moving across the period, atomic number is the significant factor for general trends, and moving down the group, the principal quantum number is the deciding factor. So where for F block elements, if they are causing shielding, the shielding obviously they are basically increased, adding into the same orbital, right? So वो कोई extra किसी shell में नहीं जा रहे. आपका exact question क्या था? Can you repeat that?
सर उसमें जब हम लोग एफ ब्लॉक एलिमेंट्स दरमियान में आएंगे ना, उसमें फिफ्थ पीरियड और सिक्स्थ पीरियड दरमियान में जो एफ ब्लॉक एलिमेंट्स आएंगे उसमें न्यूक्लियर चार्ज तो इंक्रीज होगा, जिसकी वजह से उसकी जो एटॉमिक रेडियस है जब ग्रुप से पीरियड से शिफ्ट हो जाएंगे, न्यूक्लियर चार्ज के इंक्रीज होने की वजह से क्योंकि दरमियान में एफ ब्लॉक एलिमेंट्स आ रहे हैं, वो एटॉमिक रेडियस में उतना कम नहीं आएगा.
Yeah, so
उसके दरमियान में तो इलेक्ट्रॉन्स भी ऐड होंगे.
exactly. So I got it. So that was the same idea we were discussing when we were adding D block elements, right? So here was 4s and here was our 3d, right? So electrons are being added in the lower shell and they were causing effective shielding. But due to this penetration or some probability here as well, so this shielding is not 100%. So same is the case here. Suppose if you are adding F block, right? So first F orbital starts here. It has radius, it will have radius somewhere here. And if I talk about for F and then 5s suppose, so it will be here. So yes, these extra electrons obviously adding in the inner shell will cause effective shielding, but that shielding won't be 100%. So in very simple words, there are several factors. You are going to decide which one is prominent here. Yes, atomic number is increased by 14 extra elements, which is obviously causing this to this transition to 32 atomic number increase, but due to some penetration here as well, the shielding is not 100%. Secondly, due to this higher atomic numbers, they do exhibit relativistic effect explained by this equation. So there are two factors, atomic number and relativistic effect here. And there is one factor which is shielding, obviously. So these are the deciding factors, but obviously the relativistic effect is the most prominent one.
मतलब जो न्यूक्लियर चार्ज होगा वो शील्डिंग को डोमिनेट करेगा.
Exactly, because nuclear charge बढ़ गया 32 हो गया, right? And साथ साथ electrons add हो रहे हैं, but it is not the case that every one electron adding here will 100% cancel the effect of proton here. Why? Because now we do not have the exact radiuses, right? So अगर exact radius होता तो obviously यहाँ वाला एक electron 100% shield कर रहा होता इसको. But since there is probability distribution, so that's why this atomic number dominates here, because it is increased by a significant amount, right? It's 32.
सही.
All right. Any other question? All right. So what we have discussed so far, we had discussed in previous lecture, the orbital energy is the same idea we have seen here in atomic radius as well. So now we are going to look through the ionization energies. So the general idea is same what you have studied before as well, that all these factors, orbital energies, and radius are obviously interrelated. The closer the orbital, the lower will be its energy, and same effect will be seen in ionization energies as well, because you know the ionization energy is the amount of energy required to remove the electron. You are removing electron from the obviously attraction of the nucleus, and if there is the smaller radius, it will have lower energy, or the ionization energy will be higher. Remember that when I talk about lower orbital energy, I'm talking about this one. Basically, ionization energy is minus the orbital energy. This energy is already negative. Multiply by this negative sign, this will become some positive energy. So if electron is closer to the nucleus, it will have less orbital energy, or it will have small radius, but it will have higher ionization energy. So let's go through the periodic table and discuss the same trend here. So as we go along the period, the radius is decreasing and that ionization energy will increase. So from hydrogen to helium, the general trend is being followed. And let's talk about the second period: lithium, beryllium, then boron, carbon, nitrogen, oxygen, fluorine, neon. We have already discussed these two. Why exactly the ionization energy trend deviates here? The sulfur, the oxygen, both of them. Even you can see it is translated towards selenium and here as well. But so there are two things: either the trend will decrease, completely deviates, or as you have seen in the previous slide when we were discussing about p orbital, right? So उसमें हमने देखा था कि वो radius बहुत small amount से increase हुआ था. So let me just right. So इधर हम देख रहे थे रेडियम के केस में exact trend particular exception थी, कम हो गया था. इधर हमने देखा था कम तो नहीं हुआ, but obviously same amount से increase नहीं हुआ. So we will be discussing both the factors in our later discussions as well. So particularly you are already familiar with the idea that the elements arranged in the groups do have some sort of similar properties. So when you see any anomaly or any exception in a particular group, that will be translated towards other elements, right? So this is oxygen, now this is sulfur. It has less ionization energy than phosphorus. Again, these two, you can see if it is increasing by very small amount, or it is almost the same. Here as well, it is increasing, but not increasing by the same factor again, and then the same. So all explanation stays the same. We have already discussed their atomic configuration looks like this. Once you remove this electron, so exchange energy contribution here is minus 3K. Once we remove this electron, the exchange energy contribution stays the same. And when you subtract these two values, the resultant is 0. So there is 0 stabilization anchored by exchange energy. That's why it is easy to remove electrons from this particular group. This group is basically the sixth one, the group containing the oxygen, sulfur, selenium, and so on. So that's the main idea. And why exactly it is prominent in this second period, due to this extra small size, or we have seen in the previous lecture, the second period anomaly. So due to this extra small size, this phenomena is quite considerable in the second period, but it will be translated towards other elements, as I have shown here, that the increase the increase won't be the same or the same factor as it was increasing in the previous elements. All right, so that was the first